All right, so today we're going to talk about inverse functions. So if we have a function that takes some input and produces some output, the inverse of that function takes the output and tells us what the input had to be to produce that output. So some functions have inverses and some do not. And I want to use this first example to illustrate the difference between those two cases. So in this first problem, we have a ball that's tossed straight up into the air, and we're given the function for height over time, right? So the height is in meters, the time is in seconds. Okay, so if we know the time, we can plug in the time and calculate the height. And so that's what part A is asking us to do. We're asked to find the height of the ball after 3.5 seconds. So really all we need to do is just plug in that value for t. So h of 3.5, right? We put 3.5 seconds in for t, and then we could just calculate it, right? So 3.5 squared plus 20 times 3.5, and then plus 1. All right, so you can just put that into your calculator, and I got 9.75 meters. Okay. Now, the second part of this question is asking us to find the time. How many seconds after being tossed will the bottle's height reach 16 meters? So in this part, we're given the height. We're given the output of our function, and we're asked to figure out what that t value, which is the input, which we're asked to figure that out. But we know how to do that, right? We can just set the height equal to 16, and then we want to solve this equation, right? 5t squared plus 20t plus 1. Okay, we're trying to find the t value where the height is 16 meters. So I'm just going to move everything to the left-hand side just because I like to work with positive leading coefficients. So if I add 5t squared to both sides, I get 5t squared minus 20t, and then 16 minus 1 is 15, so I have plus 15 equals 0, and now you can see it's a quadratic equation. So I also see a common factor of 5, so let's get rid of that. I think that'll make that easier. I'm just not really get rid of it. I'm going to factor it out. So then I end up with t squared minus 4t plus 3 equals 0. All right, now to solve this, I need to factor, right? I need to factor that, or I could use a quadratic equation, but this one's easy enough to factor. So if I factor it, I get t minus 1 times, t minus 3. Okay, so t is equal to either 1 or 3, and this is in seconds. All right, so I have two answers, right? I have two times when the ball reaches 16 meters. And that makes sense given the context of the problem because, you know, it's the flight of a ball. You're tossing it straight up into the air. It's going to pass 16 meters sometime on the way up, and it's going to pass 16 meters again on the way down. So it makes sense as there are two solutions. But in this case, if we try to find an inverse function for this h of t, right? If we want to find a function for t in terms of h, right? It wouldn't be a function, right? Because a function is defined to be, something that takes an input and produces exactly one output. Okay, but here we have we have two outputs, right? We would have if we had an inverse that worked, we'd have two outputs for a given input. And that would not be technically a function. So a function like this h of t function would not be considered to have an inverse. Okay, now you could restrict the domain and then just consider like the first 2 seconds, right? And then you could possibly get an inverse, but we'll talk more about that later. All right, so let's take a look at the second example. All right, and so this one is just a depreciation problem. We're given a function for the value of a car over time. So the output of this function is value of the car. The input is time. So you give it a time, it'll tell you the value. Okay. So it was initially purchased at $20,000. So you can see when t equals 0, it's 20,000. And then we can put in any value of t. So part A, we're just going to find the value after 2 years. So that's just a straightforward matter of putting 2 in for t. So we have 20,000 times 0.8 to the second power. And I put that into my calculator, and I can calculate a single value of $12,800. All right, now similar to what we did before, in part B, we're given the output and asked to find the input. Okay, so we're given, because the function's output is value, so here we're given a value of $8,000, and we're asked to find, to figure out how long it will take for the car's value to reach $8,000. All right, so that's the output, so I'm just going to write 8,000 is equal to 20,000, and then times 0.8 to the t. All right, so I need to solve for t. So the first thing I'm going to do is just divide everything by 20,000. All right, so then I get 0.4 is equal to 0.8 to the t. And whenever you have the variable in the exponent, you should think about using logarithms. Now you can use a base 10 log, or you can use the natural logarithm. And I'm just going to use a natural logarithm. So I'm going to take the natural log of both sides. So natural log of 0.4 is equal to the natural log of 0.8 to the t. All right, and I can just use the properties of logarithms now to bring that t out front. So I'm just going to copy this down. Natural log of 0.4 is equal to t times the natural log of 0.8. And then I can, the natural log of 0.8 is just a number. And so now I can solve for t by dividing both sides by that natural log of 0.8. So I get t is equal to the natural log of 0.4 over the natural log of 0.8. And that's something I can put in my calculator. And I get 4.1 years. Okay. So in this case, I get one output. I get one t value, right? And you can graph these. Let's take a look at the graphs of these two functions, because you can see a little bit better what's happening here. So for the first one, which is the height of the ball, if I gave it a value of t, right? Here I give it a value of t, I can find exactly one value of height that corresponds to it. But if I give, if I have a value of height, there are actually two values of time that correspond to that height. Okay, whereas if I graph the depreciation problem, that depreciation rate, the value over time is just a decreasing function, I give it a time and I get exactly one value. If I know a value, right, I get exactly one time. So this function for value would have an inverse, okay, because the inverse would be a function, essentially, right? Because the inverse would have one, I'm basically swapping the input and the output, and so if I give it a value, I have one. If I give it a value for the value of the car, I have one time, one and only one time that corresponds to that value. Whereas in the case of this height function, if I try to find an inverse, technically I have two different time values where that height occurs. All right, so that's the main thing. That's the main difference between a function that has an inverse and one that does not have an inverse. And so it really just depends on whether that inverse would be a function, by the definition of a function. All right, so I want you to go ahead and take a look at this next page. You can read through, what is an inverse? Remind yourself what an inverse is, which functions have inverses, There's kind of a new piece of, maybe some new to you terminology here of one-to-one functions. So a one-to-one function is an invertible function. And and this horizontal line test can be used to determine whether a function is invertible or not based on its graph. Okay, and also be aware that we can restrict the domain of a function in order to make it invertible. So like I was saying with that height function, if we just restrict our domain to the first couple seconds of the flight, then we can write an inverse for it. Okay, so so take a look at this page and I'll meet you for the next example.